Okay, hello everyone, and this is the final project presentation for DA527. So I'll be starting. I am Saptarshi Mukherjee, and I'll be starting with the first part of the presentation. So the paper we chose was Nanowire Neural Networks for Time Series Processing. It is available at openreview.net. So what is the main motivation for the paper? So the motivation is starting with the fact that nanowire networks naturally act like recurrent systems because their memory-stive junctions store and update state over time. We know that recurrent neural networks, they have an interpretation of the state that helps the recurrent neural networks to model sequences based on input and previous information. We know that neuromorphic computing benefits from physical dynamics, and nanowires physically implement these RNN-like nonlinear state transitions, and they form high-dimensional nonlinear reservoirs, which makes them ideal for fast, low training cost sequence processing, which we will see for ESNs. And in fact, hybrid NW ESN and NW RNN models can even outperform classical RNNs, which we will see later on in the results section. So some introduction to the nanowire memory star physics. So nanowire networks are meshes of tiny metallic wires whose junctions behave like synapses in neurons, and their structures can closely resemble brain connectivity. Each junction acts as a memory-stive element whose conductance changes with past electrical activity. There are some equations on this later. These dynamics mirror ion flow mechanisms in biological neurons, similar to the Hogden-Huxley model, and as a result, nanowire networks naturally function as brain-inspired computational substrates. So now some of the equations. So the state equation for the synaptic properties of the nano NW under electrical stimulation expressed in the following way. So in this equation, Gij is the normalized conductance that assumes values between 0 and 1, and we have the following equations for Kp and Kd as well, and the authors have actually adapted this for use in back propagation, and that is they have done in this way. So the authors actually have developed the nanowire neural networks for time series processing, where the physical memory state G becomes the nanowire network state. So the previous equations on this page 1, 2 and 3, they are rewritten. So equations to get equations 4, 5 and 6. So here dH/dt is Kpx. Kpx is actually a factor which increases the conductance, that is the potentiation, and Kd decreases the conductance, that is depression. So we can think of this in terms of neurons as a neuron's electric potential being increased or decreased. So dH/dt is Kpx times 1 minus h minus Kdx into h. So minus sign is because it decreases the conductance. Kp is Kp naught into e to the power eta px, while Kd is Kd naught into e to the power minus eta dx. Once again, the minus sign is for the fact that the Kd in Kd the conductance is decreasing. So these are all hyperparameters: Kp naught, Kd naught, eta p and eta d greater than 0. They are all network hyperparameters. And then we have the state transition function of a single nanowire neuron. So we discretize 4. So instead of dH/dt, we are writing it as some delta h instead of dH/dt. So we get ht plus 1 equal to ht plus delta t into kpxt plus 1 minus kpxt plus 1 plus kdxt plus 1 into ht. So you can see the parallel with equation 4 here, where ht plus 1 minus ht would have been delta h, and this delta t term into this. So we have ht, if you can rewrite this as kp xt plus 1 into 1 minus ht plus kd xt plus 1 into ht, you will get exactly this. And remember that h must belong between 0 and 1. So now we have the nanowire neural network architecture. So the same equation here, it is explained in the computational graph, which it is available in the paper as well. And we have the dynamics of the neural network described in this following way. So instead of going through exactly what the equations are, I'll summarize and say that ht indicates the state of the recurrent layer, xt is the external input, wh is the recurrent kernel, wx is the input to recurrent kernel, v is a bias vector. So some of the factors about this is that the nanowire neural network model introduces key physical hyperparameters kp0, kd0, eta p, eta d, delta t and gamma, where gamma less than 1 ensures stable eco state like dynamics. The input value is in fact they shift the system's fixed point. So we have an affine transformation in 7. The rescale function performs this affine transformation, and it helps us to keep the states in a useful operating range for the nanowire function to occur correctly. And the rescale heuristics, it improves stability and learning performance before the non-linear nanowire functions are applied later on. And the resulting architecture, it can be used both as a reservoir model and as a fully trainable RNN. So now some points about the reservoir model. So NWESN is the reservoir-based nanowire neural network in which both the kernel KWX and the recurrent kernel matrices they are all initialized under stability constraints and left untrained. So as usual in these applications, we rescale WX, the bias V, and the recurrent kernel with input scaling W, bias scaling, and the spectral radius respectively. Some intuitions about these. For example, input scaling, it controls how strongly the external input will influence the reservoir state, and large omega can amplify the input, yielding nonlinear responses at the risk of instability, while small omega increases the importance of the internal network dynamics at the risk of, however, of underfitting. While bias scaling, it helps to shift the internal state into a useful operating region because nanowire nonlinearity actually depends sensitively on the input range. When the spectral radius governs the stability and memory depth of the recurrent matrix, it is defined as the largest absolute eigenvalue of WH. Intuitively, a rho less than 1, it implies fading memory, while if rho is close to 1, it allows for longer memory with larger dynamics, although that it does run the risk of instability. And the fully trainable model NWRNN, it is different in the following way. So what it does is it extends the nanowire model into a fully trainable recurrent network. Both WX and WH are in fact optimized using backpropagation through time, just like in standard RNNs. On the other hand, here we had just initialized them based on these hyperparameter values, input scaling, bias scaling, and spectral radius. So here they are trained using backpropagation through time. Nanowire nonlinearities Kp, Kd, which we have discussed earlier, and the state update equation, they remain fixed, providing physics-inspired dynamics, and training adjusts how inputs and past states they influence the nanowire dynamics. This combines the expressiveness of RNNs with the stability and biological realism of nanowire-based transitions. Next, over to Ishan for the next part of the video.
Good morning. My name is Ishan Gupta, and today I will be discussing the implementation part of the nanowire neural network for time series analysis. So, in this part, I will be discussing about the implementation, training setup, what were the datasets that we used, what were the hyperparameters that we used during our training, and what were the baselines that we tried to reproduce. So, let's get started with the implementation. So, for the implementation part, I closely followed the architecture and methodology described in the paper and built the entire model from scratch in PyTorch. The core idea was to simulate the behavior of nanowire neural networks using a recurrent neutral framework where the hidden states evolves according to the potentiation and dynamics. So the first step was to implement the nanowire state update equations. I described the ODs using a forward Euler approximation and then incorporated the nano non-linear scaling terms that kept the hidden state stable. This formed the main update rule of both ESN and the RNN variants. Next, I created the separate modules for input transformation, the recurrent updates, and the linear output layer. For the nanowire ESN model, the input weights and the recurrent reservoir weights were handled separately, meaning that only the final readout layer is trained using the ridge regression. This setup lets us test the intrinsic computational capability of the nanowire dynamics without relying on gradient based training. For the nanowire RNN model, I allowed both the input weights and the recurrent weights to be fully trainable. This required the implementing backward propagation through time and handling sequence batching efficiently. After building the model, I integrated into a complete training pipeline. I processed all the data sets and followed the normal test and test and training split. For training neural nanowire RNN, I used the Adam optimizer and experimented with different learning states and batch sizes. For the nanowire ESN version, I tuned the spectral radius and input scaling to ensure the reservoir had the right dynamic behavior. A key part of the implementation was hyperparameter tuning. Nanowire systems have several parameters that control the potential and depression, such as K, P naught, ND, and NP, and the time step delta T. I performed a grid search to find the stable and performant combinations. Finally, I trained and evaluated both models across all datasets using accuracy for classification tasks and mean squared error for regression. This allowed me to compare the nanowire based models and assess their performance under realistic time series conditions. So these were the implementation parts. So also I used a fixed hidden size n equal to 100 for all models to ensure fair comparison. Now let's move on to the dataset part. So there are four datasets that I used for classification that we used for classification and two datasets for regression. So first four were 4-day. 4-day dataset consists of engine sensor readings collected from an automotive system under normal and abnormal operating conditions. This task the dataset is to classify each universe time series as healthy or faulty. This behavior the sequences are relatively long and contain realistic noise patterns, making this dataset a challenging benchmark for time series models. So the task for this dataset was binary classification. Next dataset was ECG 5000. So ECG 5000 contains electrocardiogram readings representing different heartbeat morphologies. It is a five class classification datasets derived from the PhysioNet BIDMC database. Each sequence is about 140 samples long and reflects subtle behavior in heartbeat shapes. So next dataset was synthetic control. Synthetic control is a basic benchmark datasets composed of artificially generated control process signals. So it includes six different types of temporal patterns, each representing a different class. The sequences are short and noise free, making this dataset ideal for assessing the baseline of classification model and understanding their capability to separate clean and well defined temporal structures. So the task was six class pattern classification. Then next comes the earthquake database. Earthquake database consists of sensor readings used to distinguish between earthquake events and non-earthquake signals. It possesses a binary classification with significant class imbalance, meaning the true events are relatively rare, and the sequences are 512 samples long. It include real-world noise and variability, making the data set valuable for evaluating a model's sensitivity to rare event detection and noisy observation time series. So for the regression part, I used flood modeling 1 and flood modeling 2. Flood modeling 1 is a real world multivariate time series regression dataset designed to predict water level dynamics in a river basin. It contains several hydrological inputs such as rainfall, soil moisture, flow rate, and other environmental variables recorded over time. So the task involves forecasting a continuous target variable, typically water level or discharge, making it a suitable benchmark for evaluating models' ability to learn long-term dependencies, nonlinear behavior, and complex multivariate relationships. So, for and also flood modeling 2 is an extended version of flood modeling 1. It is a richer collection of environmental variables and longer temporal sequences capturing more detailed hydrological behavior and across different periods and weather conditions. So the task was regression for both the datasets. Then the baselines that we tried to reproduce are these. So the authors also tried to compare their models with the baselines that did ESN and with their nanowire ESN, so they show that they have an improved performance, and also with the RNN and their nanowire RNN. So these were the results that they try to show and show their models perform good in certain scenarios. What were the hyperparameters that we used? So these were the different hyperparameters used for different models. So for nanowire ESN, we used input scaling, bias scaling, spectral radius, slope parameter, and different other parameters for different models. Like say for nanowire RNN, we there were certain more hyperparameters. One was this slope parameter S as well as batch size n. So as you can see, these were the different values, and in the future we will also show what was the we also performed best hyperparameter search, and Soumya will discuss on this more. Now hand over to Soumya for continuing further. Thank you.
Okay, so moving on to the results, let us first look at how our implementation performed on the classification task. Like we compare the four different models, like the standard eco state network and the standard RNN, and now we're two variants for nanowire variants. Now, I want to draw your attention on the 4-day dataset where you can see that the our NWRNN significantly outperformed the standard RNN cause the because of the it consists of the engine sensor readings with realistic noise, making it quite challenging, which is only captured by our nanoware architecture, and the difference is significant. Like you can see the jump in the performance. And also in the simpler data sets, our NW nanowire architecture is not lagging much behind. Like the accuracy is not very much behind, like it is at par and comparable. And again, in the earthquake where ecostate networks are more powerful, our nanowire architecture is performing quite well. Now coming on to the regression results, the in regression you can see that in the flood modeling 1 and the flood modeling 2, in both of the tasks our nanowire architecture is performing better. Since it is a regression task, so we are evaluating on our mean squared error, so the lower is the better number and it is highlighted here. So so like you can see that the flood modeling 2 task for flood modeling 2 task is not very simple. Like the task is quite challenging and the data is quite challenging, and you can see the best performing is our nanowire architecture only. This suggests that the fading memory property inherent in the nanowire physics is exceptionally good at tracking continuous environmental dynamics like water flow over long periods. So more than standard recurrent unit, it is performing quite well. Now, of course, this the performance we are talking about is not directly or chosen by random. We did a hyperparameter tuning for it, for both the models, and then evaluated it. And as you can see that the what are the sweet spots of a model? Unlike a standard neural network where you can mainly tune the learning rate, the nanowire network is a physical simulation. We found that the model is particularly sensitive to the input scaling and the spectral radius. For example, for the nanowire ecostate network, we found that the spectral radius of zero point 0.9, you can see that the zero point 0.9 is the tuned result, and the input scaling factor of 1 provided the most stable region of the operation. And also, if these values are too low, the signal dies out, and if they are too high, the simulation becomes chaotic. Finding this balance was very much actually critical to achieving the high accuracy scores you saw on the previous slides. Now, coming to the insights, what the other insights which we can draw is that the nanowire equations actually naturally projects input into a higher dimensional space. So it almost acts like a kernel, like it projects the data to a higher dimensional space, making it very much easy for temporal patterns in the for the networks to identify. So these are the first rich intrinsic dynamics is covered, and in the like it has a built-in stability like memory plus non-linearity balance. Like standard RNNs often suffer from exploding gradients, but for nanowire architecture, it is not the case because the equations include the physical saturation limit. This prevents the value from blowing up during training, leading to more stable convergence. Now, memory nonlinearity balance. Finally, the potentiation and the depression mechanism creates a natural balance between remembering the past and reacting to new inputs, which is exactly what is needed for time series processing. No, but are our are this is this architecture free from limitation? No, there are certain limitations also. Like the hyperparameters are too much sensitive. Like nanowire dynamics depends upon very much is highly dependent upon the hyperparameter, and it is quite sensitive with respect to the depression rates and the scaling factors. Also, the ODE based approach are costly, like it requires a numerical integration for every computation at every time step, which is very costly to do as compared to the recurrent neural networks. And the performance was also not always superior, for the for the simpler data set or for the short sequences, the nanowire models cannot outperform the LSTMs and GRUs and even the equostate networks. Scalability challenge are also inherent in our nanowire architecture is that the hidden dimensions are typically small, like 50 to 100, and scaling to 100 and 1000 units may cause numerical instability with respect to the training time. So, what can we conclude? Like our project explored uh, both the variants of our nanowire neural networks, like the ESN and the RNN, and evaluated them on a diverse collection of data sets also. But we demonstrated that despite being on the simple physical equations, these bio-inspired models can outperform classical RNNs on complex, noisy tasks like the 4D dataset, which I talked about earlier. They offer a promising alternative that is inherently stable and physically grounded. Now, looking ahead, we believe the future of this research lies in the hybrid architecture instance. For instance, combining the short-term memory dynamics of nanowires with the long-term attention mechanism of transformers could solve the scalability issues which we were facing, like I talked about it in the limitations. Now, I think that it can be improved by combining it with a much powerful architecture, like our physical dynamics model with the current state of the art architectures. So that was all for this course project, and I would like to conclude it. So thank you.